Good afternoon, everyone. Welcome to join us the Urban Flood Modeling and Risk Management webinar again. Today we are very happy to have our colleagues at Center for Water System at University of Exeter, Dr. Chris Sweetapple. He's going to talk about Safe&SuRe urban water management. So I will hand this to Chris.
Okay, so yeah, I'm going to talk about Safe&SuRe water management. So just to give a bit of an outline, I'd start off with what is Safe&SuRe, what does it stand for, look at why we're doing it, why it's needed, then want to introduce the Safe&SuRe framework, which is what we're using to address the problem, and then want to run through a few of the key concepts we've been working on and some example applications. So the what? So SAFE stands for reliable, which essentially is how systems have been traditionally designed. So we want to be reliable and not to fail. There's increasing recognition that sort of with the uncertainties we're facing, future threats, we can't avoid failure in all circumstances, and we need to think about how we're going to be resilient and also sustainable. So that's the SuRe element. So the overall aim of the Safe&SuRe research project is to develop a new paradigm for Safe&SuRe urban water management in the UK in response to emerging challenges and global uncertainties. So it's an EPSRC funded project lasting 5.5 years. It's due to finish at the end of August this year, so we're coming up to the end of the project. And it's led by Professor David Butler, along with Razia Farmani, Grant Alfu and Sarah Ward. So in terms of why we're doing it, it's becoming increasingly recognised we're facing lots of challenges in the water industry, ranging from global warming, population growth, urbanisation, changing demographics, and we've got things like cyber security. So all sorts of threats that we might have to deal with in the future. And as well as these, we've also got the increasing variability we need to deal with. So in terms of how we're going to address this in the Safe&SuRe project, we have an interventions framework that we've developed that sort of forms the foundation of most of the work. So this is used to show how threats can ultimately result in some sort of consequences, and it helps us to identify different opportunities for intervention. So I'm going to try and illustrate this with an example. So for a threat, we might have climate change, and then this might affect the system, the water system in some sort of way. So for example, we might have increased flows in a watercourse. This could then have some sort of impact, so that might be flooding, and then that may or may not have some sort of societal, economic or environmental consequences. So for example, with flooding, that might result in damage to property. And then using this framework, we can try and work out how we might reduce the consequences resulting from any given threat. So firstly, we could look at the intersection between the threat and the system, and our first opportunity to intervene here is called mitigation. So we've tried to sort of define all of our interventions very precisely to make sure we're all using the same language. So mitigation we've defined as any physical or non-physical action taken to reduce the frequency, magnitude or duration of a threat. So essentially what we're trying to do here is reduce the size of a threat. So if climate change was our threat, we might try and mitigate it by reducing our greenhouse gas emissions, and so then hopefully we'll reduce any effects on the system. However good our mitigation measures are though, we're still likely to have some effects on the system. So then we need to move a bit further around the framework, and we could start thinking about the intersection between the system and the impact. And our intervention here is called adaptation, which is action taken to modify specific properties of the water system to enhance its capability to maintain levels of service under varying conditions. So essentially what we're trying to do here is minimise the impact. So coming back to our example, if we've got increased flows in the system, we might need to build flood walls, and then hopefully we'll minimise any flooding results from these increased flows. So these adaptation measures have to each address specific system failure modes. And then, as before, however good our adaptation measures are, there are likely to still be some impacts at some stage. So with whatever adaptations we want to use, there will probably still be flooding sometimes. So our next opportunity to intervene looks at the intersection between the impact and the consequences. And this intervention we've called coping, defined as any preparation or action taken to reduce the frequency, magnitude or duration of an impact on a recipient. So essentially we're just trying to minimise the consequences of any given impact here. So back to the flooding example, if our consequence is sort of damage to the property, we might try and introduce sort of property level flood mitigation measures to try and minimise these consequences. So that would be an example of a coping measure. Then still, however good our coping, at some stage there will probably still be some consequences. So lastly, sort of completing the circle of our framework diagram, our last intervention is learning, which is embedding experiences and new knowledge in best practice. So essentially that's reviewing all of our interventions and improving them for the future. So now we've got this framework, there are several different ways we can use it. So we can work with a top-down approach, a middle-based approach, a bottom-up approach, or a circular approach. So just to look at each one in a little bit more detail, starting with the top-down approach. So this starts with the threats and focuses on mitigation of these threats. So this is the sort of conventional approach that would be used in risk assessment, and it's good for addressing responsive systems to changes that we can reasonably predict. The main problem here, though, is that it relies on us being able to identify the threats. So it's not so good for threats we can't foresee, or perhaps ones that are very uncertain or we don't know probabilities of. So yeah, what about the threats we don't know about? So next up we have a middle-based approach, which is focused instead on the system failure modes, irrespective of what threat might cause them. And then next we have a bottom-up approach, which is focused on the consequences and the coping. So this relies on us being able to identify possible consequences and then come up with coping measures for these. And again, this doesn't need detailed knowledge of the threats or the impacts. And lastly, we have a circular approach, which is very much focused on the learning. So evaluating the success of all our other interventions, our mitigation, adaptation and coping actions, and ensuring that our strategies and actions are updated. So I thought next I would introduce a few of the key concepts developed as part of Safe&SuRe. So firstly, looking at the concepts of reliability, resilience and sustainability, and how these three things are related. So in Safe&SuRe, we start off with reliability. So we've got a definition here. So reliability, the degree to which the system minimises level of service failure frequency over its design life when subject to standard loading. So this is sort of like the baseline, is where we want to start. We design our systems to be reliable. Once we've got that, we need to start thinking about resilience. So the degree to which the system minimises level of service failure magnitude and duration over its design life when subject to exceptional conditions. So the exceptional conditions is the key bit here. And then building upon that, we have sustainability. So the degree to which the system maintains level of service in the long term whilst maximising social, economic and environmental goals. So if we look at this pyramid, we could say that in order to be resilient, a system first needs to be reliable. In order for it to be sustainable, it needs to be reliable as well as resilient. We can also look at the different types of events that are addressed by reliability, resilience and sustainability. So this plot here shows sort of like the relationship between magnitude and probability of different events. So our low magnitude events tend to be highly probable, our high magnitude events very low probability. So reliability tends to address our sort of everyday events, or at least those that are expected to occur within the design life of the system. So these tend to be our low magnitude, high probability events. I'm also showing risk here because that's something else that's often used sort of as alongside resilience. The two are sometimes confused. So risk tends to address our higher magnitude events, but it can only really be used for those that we can assign a probability to, or at least those that we can anticipate. It's not so good for our real extremes, so the things we never knew were coming, or we've got no idea how likely they are. So really that's where resilience comes into its own. So resilience can address extreme events, including those that can't be anticipated or can't be assigned a probability. So perhaps including our so-called black swan events. And then sustainability on top of that, it addresses the whole life of the system, so really it needs to capture all of those elements. Okay, moving on to global resilience analysis, which is a method that we've developed for evaluating resilience, that sort of building on this the idea that resilience needs to address extreme events. So we use a stress-strain type concept to address resilience, where we stress a system and measure the strain that results from it. So we capture the effects of everything from a very small stress right up to a really large stress, however improbable it might be. So our stress might be, if we're looking at a sewer system, for example, it might be the number of pipes in the system that are blocked. So we could start from 0 pipes blocked right up to 100% of pipes in the system blocked, however unlikely that might be. And then our strain would be some measure of the level of service failure. So, for example, flood depth. So this red line here represents a vulnerable system because a small stress results in a very large strain. Ideally, what we want is something more like this green line, which would be a much more resilient system. It can withstand a large stress and with just a small strain. So this is an example of a middle-based approach because our stress here is a system failure mode rather than a threat. And then we're looking at the impact of this system failure mode. So an example of how we might use this, so this is a piece of work looking at the effects of different adaptation measures in an urban drainage system. So we might adapt our system by providing centralised storage, or we might provide decentralised storage, and then our impact could be measured in terms of flood volume. So some example results here. So these are our stress-strain type curves. So on the x-axis we've got the percentage of pipes in the system that have failed, sort of from a very small stress magnitude right up to the maximum theoretical possible. And then on our y-axis we've got our flood volume. So you can see the black line represents the base case, so the unmodified system. Red line shows what happens if you introduce centralised storage. The blue line, what happens if you introduce distributed storage. So you can see that if we looked at sort of under normal conditions, so 0 pipes failed, both of the interventions provide some improvement. But when you start looking at our larger stress magnitude, so our larger proportion of pipe failures, only the distributed storage provides much benefit. So you could say from this that providing distributed storage is a much better way of increasing the resilience of the system. So that's an example of how we might use global resilience analysis. The next concept I wanted to introduce was the distinction between properties and performance, which is something we've worked on quite a bit. So we have our definition of resilience, which is the degree to which the system minimises level of service, failure, magnitude and duration over its design life when subject to exceptional conditions. So we could say from this that the goal of resilience is to minimise the magnitude and duration of failure. So this is telling us what the required performance is. It's not telling us how to achieve it. So how to achieve it is where the properties come in. So for example, we might improve the performance by increasing redundancy in the system, or perhaps something like connectivity. So these are often things that are associated with resilience, but actually they don't guarantee an improvement in performance. So we've done a bit of work looking at the relationship between the properties and performance of a resilient system. So one of those is working on a set of 250 sewer system case studies, and looking at properties and performance in each one. So we've done a global resilience analysis of each of these systems, looking at the resilience to pipe failure. And then also evaluated lots of different properties of the systems, and focused on imperviousness in the catchment, so trying to relate this to resilience, and also storage in the system. So I've got a few results here. So this plot is showing the resilience to pipe failure of each of those 250 case studies. So on the x-axis we've got a measure of distributed storage, which is a property of the system, and on the y-axis we've got the performance of each system. So you can see from this that property and performance are related, but actually it's only a fairly weak correlation. So this was looking at the relationship between distributed storage and resilience. We can do similar for looking at the relationship between imperviousness and resilience. And this time you can see that there's next to no correlation between the two. So we can sort of see from this that providing a specific property, while it might be useful sometimes if we're trying to improve resilience, we can't guarantee that providing any given property will improve performance. Okay, I've come to my sort of wrapping up. Just a few key messages. Firstly, one thing we've really sort of tried to push in Safe&SuRe is the importance of having clear and consistent language. So, for example, resilience is given lots of different definitions by different people. It's important really that we all need to be on the same page. And then also sort of when we're working with the framework and all our different types of interventions, it's important we've all got an understanding of what each one means and we're using them consistently. Also, it's important that resilience addresses extremes, so not just our everyday events, which really should be captured in reliability. We need to capture the absolute extremes, also including those that we can't very easily consider in a risk assessment. And then also that providing specific properties doesn't necessarily guarantee resilient performance. So, for example, providing redundancy, whilst it might be assumed that that's going to provide resilience, that is by no means guaranteed. And lastly, just really to summarise some of the key things from Safe&SuRe. So Safe&SuRe provides a framework that links threats to consequences. It provides a set of clear and consistent definitions. It allows us to carry out analyses in different directions, so for example our top-down, middle-based, bottom-up and circular, and using these it allows us to develop a range of different strategies to increase resilience. It allows us to carry out a comprehensive resilience assessment with no knowledge of the threats, using global resilience analysis. And lastly, it allows us to identify critical components in systems and identify key opportunities for intervention. And that is it. Thank you very much. If you've got any questions, I'll be happy to answer them.
Thank you very much, Chris. It's very interesting. Any question from our audience?
I have a question.
Yep.
Thank you, Chris. Very interesting presentation. So it seems quite a broad framework, and whilst it's probably quite a good idea that everybody uses the same definitions for resilience, I'm not sure everybody out there is. What has the project done to try and get everybody on the same page, if you see what I mean?
Yeah, good question. I think getting everyone on the same page is a massive challenge, as you say. There's like so many different people working on it. We have been working with water companies and running some workshops. So yeah, trying to sort of promote a good understanding of resilience, and I think that is getting across. So, for example, we've held workshops with Scottish Water and Southern Water, and I think they found it very useful to see the framework and yeah, sort of try and understand how we're viewing resilience, and try and come up with a more consistent understanding, really.
I did like the definition of the goal in there to minimize duration and something else, but dual objective
Magnitude and duration
gives us something interesting to possibly optimize in the future.
Yeah.
Okay, thank you.
Thanks, Mike.
Thanks, Chris, for the presentation. It's Julian from Innovize. I've got just one quick question.
Mm-hmm.
So it seems you, in your analysis, you've focused on distribution and drainage networks. I was wondering if you have looked at other water infrastructures, or if there's any plans to look at other infrastructure. I was just thinking about dams, for example.
We've done quite a bit on water distribution systems. So water distribution and our sewer networks have been our main two at the moment. But as Mike said, it's quite a broad framework, and actually we hope that sort of like the concepts could be applied much more widely without too much difficulty.
Okay, so it will be maybe a follow-on project looking at other infrastructures.
Yeah.
Okay, thank you.
Thank you.
Thanks, Julia. Chris, may I ask one question? That you look into different, if you look into the different system in the different part of your urban water system, you might have different aspect properties for different systems. So how do you integrate them, and how to come up this kind of overall assessment of this, how the system is resilient, for example, for resilient to flooding, resilient to drought, etc. So how to integrate this together?
Yeah, well, I think any sort of systems analysis, you have to draw some boundary. You have to decide where you're going to, where the edge of your system is, what the limits of your study are. We have done some work on general resilience assessment. So the assessment I showed here was specified resilience. So you were looking at resilience to one specific failure mode, or resilience of one level of service to one specific failure mode. I've also done some work on general resilience, where you're looking at resilience of lots of different levels of service to lots of different system failure modes. So there has been some work sort of expanding this approach to come up with a much more comprehensive view of resilience.
So when you look into this general overall assessment, do you try to weight them different type of failure mode, and how system is resilient to different types of failure mode, or you cannot?
We haven't weighted anything, because sort of like one of the key things with resilience is we're looking at our extremes, including those that you can't assign a probability to. So we're trying to stay away from a probability-based approach.
So would it be kind of more or less the kind of yes or no, is this system is resilient to this failure mode?
I think it's all relative. You can say it's more resilient or less resilient. There's no absolute.
Okay. Any more questions? If not, I would like to thank Chris again for this very interesting talk, and thanks everyone for joining us, and hopefully we will have another webinar soon, and see you next time.
Thanks, Albert.
Cheers.